In this video, we're going to look at some vector application problems. In example 1, we're asked to find the component form of the vector that represents the velocity of an airplane descending at a speed of 100 miles per hour at an angle 30 degrees below the horizontal. Anytime we're asked to find the component form of a vector, to do that, we'll need the magnitude and the direction of the vector first to be able to transfer that into component form. So if you'll remember from previous videos, we're told that sometimes the magnitude is given as speed. So right here is our magnitude, 100 miles per hour. And then we have it at an angle 30 degrees below the horizontal. That's going to give us what we need to find our direction. Okay, now if you think about the coordinate plane, and we think about our x-axis being the horizontal, if we're 30 degrees below the horizontal, most of our angles start right here at the 0 degree mark, and we're going 30 degrees below. That's like a negative 30 degree angle. So think about the angle that we're really at. If we're going in a negative direction 30 degrees, we're actually at positive 330 degrees if you're opening this way. So 330 is what we really want to use when we transfer to component form. So remember how to transfer to component form. We put our magnitude out front, 100, and then in our vector brackets, we put the cosine of the angle first, we put the sine of the angle second, and then if this is a unit circle angle, we go ahead and put our exact answers here from the unit circle, and then we distribute our 100. If it's not from the unit circle, then we'll use our calculator, but this one is. So what is the cosine of 330 degrees? It's the square root of 3 over 2. What's the sine of 330 degrees? It's negative 1/2. And then we're going to distribute the 100 to that. Remember that the 100 goes to the numerator. So we have 100 square root 3 over 2. And we have negative 100 over 2. And then that simplifies. Those divide to give you 50. So we have 50 square root 3. And we have negative 50. That's the answer that you want unless you're told that you're allowed to get a decimal. Okay, example 2. A ball is thrown with an initial velocity of 70 feet per second. There's your magnitude. At an angle 40 degrees with the horizontal. There's the direction that you need. Find the components. So that tells you you're going to component form of the velocity. Specify which one is vertical and which one is horizontal. Okay, so our magnitude is 70. We're going to put that out front. This time our angle is 40 with the horizontal. It's positive. It's positive. We're not going in a negative direction. So it's just 40. We don't have to change our answer or our angle to a positive angle or anything like that. It's just 40. So it's going to be cosine 40 and sine 40. And this is not from the unit circle, so we will have to go to the calculator. All right, so we're going to distribute that 70 to both of these. We're going to type in 70 cosine of 40, which is 53.6. I'm just rounding to the nearest tenth right now, unless you're specified to do otherwise. And then 70 sine 40, 44.995. So because of that double 9 right there, that's going to round me up to 45.0. And then it says to specify which one's vertical and which one's horizontal. Well, this one's your horizontal one, because that's in the X spot, and then this one's your vertical one, because that's in your Y spot. And example 3. This one's a little more intensive. So you have forces of 48 pounds, 70 pounds, and 100 pounds that act on an object at angles of 30 degrees, 120 degrees, and 135 degrees respectively. Find the magnitude and direction of the resultant vector. Okay, first of all, when you're asked to find the resultant vector, that means you want to add vectors. Okay, But in order to add vectors, they have to be in component form. You can't add vectors by just adding their magnitudes together and adding their degrees together. That doesn't work, okay? So the vectors have to be in component form first. So we're going to do what we did up here in these first two examples. We're going to take these magnitudes and these directions, and we're going to transfer all three vectors into component form so that we can add them. Now, because it says respectively, that means this first magnitude goes with this first angle, and then the second magnitude with the second angle, and so on. All right, so let's line this up. The first magnitude is 48, and it's going to go with 30 degrees. So we have cosine 30, sine 30. Second vector, I'm going to go ahead and put a plus sign here because we know we are going to add these. The second vector has a magnitude of 70, and then its angle is 120. Cosine 120, sine 120. And then our third vector has a magnitude of 100, and its angle is 135. Cosine 135, sine 135. All of these are from the unit circle. Okay, so let's go back and plug in our unit circle values. The cosine of 30 is the square root 3 over 2, and the sine of 30, 1/2. All right, if we simplify, if we distribute our 48, we get 24 square root 3, and we get 24. Okay, so there's our first vector. Second vector. What is the cosine of 20? The cosine of 20 is negative 1/2 from the unit circle, and the sine of 120 is square root 3 over 2. Okay, if you distribute that 70, you're going to get negative 35, and you're going to get 35 square root 3. And then the 100. What's the cosine of 135? It's negative square root 2 over 2. And what's the sine of 135? Square root 2 over 2. Distribute the 100. You're going to get negative 50 square root 2. And then you're going to get 50 square root 2. Okay, so far, I've used all unit circle values. All of my vectors are exact. I haven't gotten any decimals yet. Okay, now when I go to add all these together, I don't have like terms anymore. If I look at all my first components, I've got a square root 3 here, and then I have just a regular integer here, and then I have a square root 2 here. These are not like terms, so I am going to have to use my calculator and get a decimal value here. I'm going to keep 4 decimal places because when I add all these together, I'm going to get a weird vector, okay, a weird component vector. That's not my final answer because my final answer asks for the magnitude and direction of my resultant vector. So once I get this big vector, I then have to find the magnitude and the direction of it. So I want as many decimal places as possible so that when I find my magnitude and my direction, I'm as accurate as possible. So the rule of thumb is to keep at least 4. So I am going to use the calculator now, and I'm going to keep at least 4 decimals. 24 square root 3. I'm going to put minus 35 since it's negative, and then I'm going to put minus 50 square root 2 since it's also negative, and I get negative 64.1415 for the first component. Okay, now I'm going to do the second component. I've got 24 plus 35 square root 3 plus 50 square root 2. And I get 155.3325. Okay, so technically that is my answer. That is my resultant vector. It's just that I need the magnitude and the direction of that now. So let's find the magnitude. Remember that the magnitude is the square root of each component squared. So I'm going to do negative 64.1415 squared and 155.3325 squared. And I'm going to type all that in the calculator. and I get 168.1. 168.1. Oops. And this was in pounds. So that is the final magnitude. Okay. Now I need to find the final direction, and that's where we use tangent. So we say the tangent of theta is y over x, or second component over first component, 155.3325 over negative 64.1415. That is definitely not from the unit circle, so we're just going to type it in our calculator. This is where we type tan inverse, remember. Anytime you're finding an angle, it's tan inverse. So second tan, 155.3325 divided by negative 64.1415. Close off the parenthesis. My calculator is giving me negative 67.6 degrees. Okay, negative 67.6 degrees. All right, so remember, we've got to see if this angle makes sense in our problem or if we need something in a different quadrant. This is quadrant 4, okay? I'm going to sketch out a coordinate plane here. If we're looking at a coordinate plane, negative 67.6 means we're going down into quadrant 4, so we're like down here somewhere. Quadrant 4, negative 67.6. Look at where our original angles were. We had a 30-degree angle, which is about right here. We had a 120-degree angle, which is about right here. And we had a 135-degree angle, which is about right here. So typically, I'm sorry, I'm saying angles, and they are angles, but these are vectors, okay? Typically, when you add vectors together, it's like you take those vectors and they kind of smush together, and the direction they end up going in is somewhat of an average between those vectors. So it seems unrealistic to me that these three vectors would end up going in this direction way down here. So I don't think this is the right quadrant. So if this is a negative tan, okay, looking at this right here, this is negative by this negative sign. What other quadrant is tan negative in besides quadrant 4? Tan is also negative in quadrant 2. It seems a lot more realistic to me that these three forces would end up in quadrant 2, since two of them are already in quadrant 2. Seems much more realistic to me that they would end up over here in quadrant 2 than ending up down here in quadrant 4. Okay, so we're going to use this reference angle, this negative 67.6. That's how far this angle is from the x-axis. We want to use that same 67.6 degree reference angle, except positive, and we want to go up into quadrant 2 and find our quadrant 2 answer. So the way that we do that, since quadrant 2 is smaller than 180, and 180 is the closest side of the x-axis to quadrant 2, we're going to take 180 minus 67.6, 180 minus 67.6, that puts us in quadrant 2, and that's the angle that we want, 112.4. 112.4 degrees is the direction of our resultant vector. So always second guess what the calculator gives you. Always make sure that the calculator answer makes sense for the problem that you're doing.